Let's take a look at a real quick example here. Um, let's evaluate this double integral of x, y, z ds, where s is given by u equals, x equals u of cosine v, y equals u cosine, sine v, z equals u, where u goes from 0 to 1 and v goes from 0 to pi over 2. So from this, obviously, my parameterized surface R uv is going to be u cosine v, u sine v, and u. So the partial with respect to u is simply going to be cosine v, sine v 1. The partial with respect to v is going to be negative u sine v, u cosine v 0. So I know that I'm going to need this cross product. So r, the partial of u, cross the partial of v is going to be, let me see, I, j, k, cosine v sine v 1, negative u sine v u cosine v 0. And let's go ahead and do this cross product. So I'm going to have 0 minus u cosine v I plus u sine v j plus u cosine squared v minus that's plus u sine squared v k, where obviously this is just going to be u, because if I factor out the u, I get cosine squared plus sine squared, which is 1, so it's u times 1. So I guess I could just quickly rewrite this as negative u, let's put it in vector form, u cosine v, u sine v, u. The magnitude of r cross u, or the partial with respect to u cross the partial with respect to v, is going to be equal to the square root of, see, this is going to be negative u cosine v squared plus u sine v squared plus u squared. Well, here, when I expand this, I'm going to, if I factor out a u squared from both of these two, I have u squared times cosine squared plus sine squared, which is 1. So I'm going to have u squared plus u squared, which is obviously the square root of 2u squared, which is u root 2. So the double integral over the surface of x, y, z ds is equal to the double integral over the parameter domain of f of this guy. So that's just going to be u cosine v times u sine v times u. This right here is my f of the vector function times the magnitude of the cross product, which is u root 2 dA. Well, this is going to be equal to the double integral, and I'm going to come back and do my bounds in just a second. I'm just going to work on this for a second. I have, see, 1, 2, 3, 4. I have u to the fourth. And root 2, I'm just going to yank that root 2 out here someplace. And then I'm going to have cosine of v, sine of v. And I'm going to integrate this. I need to put in those bounds now. So if I do, I don't know, let's do du dv. It doesn't really make much of a difference. If I do du dv, u went from 0 to 1, and v went from 0 to pi over 2. So this would be 0 to 1, and this is 0 to pi over 2. Well, looking at this, this is going to be u the fifth over 5 from 0 to 1, which is just going to give me a fifth. So this is going to be the integral of root 2 over 5. I'm sorry, root 2 over 5 times the integral from 0 to pi over 2 of sine v, cosine v, dv. Well, if I do just a standard u substitution, be careful. I mean, I had used these u's here, and I'm doing a u substitution now. There's actually different u's, so don't lose track of that. You may want to call it a t substitution or something. Doesn't really matter. Anyway, I'm going to let u equal sine v, then du equals cosine v, cosine v dv, which is exactly what I need. So I'm going to end up with the integral of u du, which gives me u squared over 2. So this is going to ultimately give me the square root of 2/5 times u squared over 2, which is sine. So sine squared of v over 2. Evaluated from 0 to pi over 2, which sine of pi over 2 is 1. So this is just going to be root 2 over 10 minus 0. So the solution is going to be root 2 over 10.